Hi, welcome to a new virtual tour of the European Southern Observatory, or ESO. My name is Farid Char, and with the producer, Felipe Zurita, we will guide you on this journey through ESO's La Silla Observatory. I am one of the tourist guides of Paraná Observatory, actually, and Felipe is one of the guides of La Silla. So regarding me, I have more than 10 years of experience doing tours in the Banana Observatory, and also some experience with outreach and education in astronomy in an astronomy center in the University of Antofagasta. So today I am not alone. We have Felipe Zurita. He will be acting as a producer. So good morning, Felipe. How are you?
Good morning, Farid. Hello, everyone. My name is Felipe Zurita. Today, I'm the producer. I have a degree in astronomy, and I love sharing science and astronomy with people. Today, I will be the producer for this online tour, and I'm excited to help bring this experience to you. So, let's go, Farid.
Okay, thank you, Felipe. So, well, just to give you an introduction, ESO would like to join you during this virtual tour, taking astronomy directly to your home or wherever you are. So, remember that you can send your questions or comments during all this streaming. Um, I imagine that maybe you have some questions already, so you can use the comments section in the Facebook or YouTube, and we are going to answer all your questions about this experience. So you can also give your name and city, country. So we are going to share this information just to announce where are located our virtual visitors. Okay? Okay, and also please don't forget to share this experience if you enjoy it. You can share simply using the buttons on Facebook or YouTube. Okay. Okay, so now we are going to start with this experience. And let's begin with the European Southern Observatory. We are going to present some information about what is the ESO. Okay, so in this picture, you can see some information about the organization. ESO is an intergovernmental organization composed by 16 member states. Its headquarters are in Germany, and Australia has recently become an strategic partner. Chile is the host state and home of all ESO observatories. Since the 60s, with the purpose I mentioned, ESO chose one of the best places on the planet to carry out astronomy, the Atacama Desert in Chile. At that time, Chile had started a site exploration campaign to attract international observatories, such as ESO to our country. So Chile offered land, and ESO chose the area that seemed best. So ESO's mission is to design, build, and operate astronomical observatories. What for? To enable important scientific discoveries and foster cooperation in astronomy. Now we are going to share a picture with the observing sites of ESO in Chile. So first we have the Paranal Observatory. This observatory is home to the Very Large Telescope, or VLT, currently the most advanced visible light telescope on the planet. In the future, the Paranal Observatory will also host the Extremely Large Telescope, or ELT, which will become the world's largest visible light telescope. And also we have the CTA, and this is an array of telescopes for the detection of gamma rays. We also have Chajnantor, the site where the ALMA and APEX radio telescopes are located. ESO participates in these radio astronomical observatories with its international partners. And finally, we have La Silla Observatory. This is the site we are going to visit today. This was the first observatory built by ESO in Chile, 2,400 meters above sea level in the region of Coquimbo. So we will go there virtually during the next hour. Okay. So now let's travel to La Silla Observatory. Okay, so now we have this virtual um, experience. We have uh, now we can look at our planet, and we are starting our journey in Europe. Since I must mention that ESO is a European organization. On this map, outlined in white, we can see the different ESO member states. Now, Chile is the host country and home to all ESO observatories. To see the sites, we will travel to the Chilean mountain range. As we move over to the Atlantic Ocean, let me tell you more about ESO's mission. To give you an idea, ESO tries to devise which type of instruments are needed to study the universe, and then ESO will design the pieces, the wheels, and is going to build and operate the telescopes, responding to observational requests from different organizations on Earth, and encouraging cooperation in astronomy. So now we are almost there. We are approaching to the Atacama Desert in Chile, and you can see in a few moments that we have an amazing desert. We are almost there. And now you will see a mountain range with domes, okay? So look at the shape of this hill. Does it remind you of anything? Perhaps a horse saddle? In fact, the mountain itself and the observatory were named after a saddle for a horse riding, okay? So over the years, La Silla has become the perfect viewpoint for studying the universe. In this video, we can see the different telescopes located at La Silla Observatory. We can see the names, such as the MPG ESO 2.2 meter telescope. We will see another one, the ESO 1 meter Schmidt telescope. And slowly we are approaching to the main telescopes of this complex. One of them is located there, the NTT, or New Technology Telescope. The CEST is a former radio astronomy antenna. And finally, we're approaching to the main telescope of La Silla. Okay, we have one more, the Swiss 1.2 meter, Tarot, the visitor center, and finally the ESO 3.6 meter telescope. So, regarding some history about La Silla, it was chosen by the astronomical community as an observational site at the beginning of the 60s. La Silla enjoys a large number of clear nights per year, a still and dry atmosphere, and dark skies, far away from artificial light sources, which exist in cities. So, the observatory was officially inaugurated by ESO in 1969, and some of the telescopes seen on the picture are now out of service. Okay, so currently we have a few telescopes in operations, and in a few months we are going to visit the most important ones. Okay, so now we are going to visit in first place this one. Okay, we are going to visit the ESO 3.6 meter telescope, and basically the name refers to the diameter of the main mirror, 3.6 meters. Okay, so we are going to visit this telescope in first place, and we are going to take a look at the main features, and we are going to understand better how this telescope works. Okay, okay, and just to let you know, this is the view from La Silla. It's a nice view, of course. Well, in this picture we have some clouds, but of course sometimes, most of the time, we have clear skies, and we have a nice perspective of the telescopes located in this observatory. So now we are going to start with this one, and we are going to take a closer look. Okay. Okay, so here we are inside of the ESO's 3.6 meter telescope, or 360, as it is commonly called by the staff at La Silla. So, as I told you before, the name refers to the mirror's diameter. So, back in the mid 70s, it was one of the largest telescopes on Earth. Currently, it hosts an exoplanet hunter. Its name is HARPS, and this is a highly specialized instrument used every night to search for other worlds outside our solar system. What do you notice about the dome from the inside? It's huge, right? It's a huge, huge dome. The altitude from the first floor to the dome is 25 meters. So you can see the size of this big facility, and basically all this structure of the telescope is equal to a seven-story building. So everything seems small here as compared with the telescope. For example, can you see something over here? Can you see something here? Well, we can see a person. Can you see? I will do a close-up so you can take a look. So we have a person here to give you an idea of how big is this telescope, how big is this dome compared to a person here. Okay, so this is a general perspective, a general view of La Silla. Okay, this telescope is located at an altitude of 2,375 meters above sea level. So this is the highest building at La Silla Observatory. So the person, as I told you before, is just below the blue structure, and this reference help us to distinguish the telescope itself from the rest of the structure. Okay, which you will now see in detail. So now I will share with you a picture uh, about this place. Let me try to find the picture here. Okay, here. Okay, so we have a picture at this side, and I want to explain basically three things we can see on the right side picture. First, in dark blue here, we can find the structure supporting the telescope itself, basically the mounting of the telescope. Okay, the mounting works as a huge arm supporting the telescope, and it includes several systems that provides power, such as electricity. On this arm, parallel to the Earth rotation axis, the telescope moves to follow objects in the sky during the observation. Now, if we go upwards, in lighter blue, here, okay, we have the telescope's body, which holds the 3.6 meter or 360 centimeters main mirror and the secondary mirror. So where's the main mirror? It is not visible because it's covered by its protection system, this black structure. This is a system of tabs which open and close to protect the mirror from dust or moisture while the telescope is at rest. In the black tubular structure here, in the upper part, we have the secondary mirror, which gathers light from the main mirror in a beam and direct it to the instruments that analyze this light. You will notice that the main mirror has a hole in the middle here. So the light is sent to the instruments through it. Okay, so we have the primary mirror, secondary mirror, and when we have the reflection in the secondary mirror, the light is going through this hole. And where's the instrument? Well, the instrument, in this case HARPS, the exoplanet hunter, is not visible because it's completely isolated in another room, on another floor of this building. So the 360 began operations in 1977, and from the beginning it represented a challenge for engineering and for ESO as an organization. European astronomy gathered talents from several countries to build an optical telescope in the 4 meters category, and the largest and most advanced category that existed at that time. So why was such a large telescope needed? In astronomy, objects are analyzed through the light, right? So the more light we collect, the more we can learn. In this case, a bigger mirror will capture more light, and therefore more information will be available. we will be able to see fainter objects and smaller details. Now, how do you think this big, giant telescope moves? So here we can see a short video to take a look at this. Felipe, do we have this video?
It's too slow movement,
Yeah, it's a
too
very
noisy
slow
and
movement.
slow.
Yes, yes, that's correct. Okay, so this is more or less how the telescope is working when it's moving. So basically, a mirror for astronomy is not just any mirror, since its shape and surface must be perfect at the scale of fractions of thousands of millimeters. So to achieve this in the 70s, an extremely thick mirror was manufactured, 53 centimeters thick on average. But this also implies an extremely heavy mirror. The mirror weighs 11 tons. This is the equivalent of two African elephants. So if we want to build larger telescopes, we need to find other solutions. So how was the next step taken? We will see it later with NTT, the New Technology Telescope. Okay. Okay. Felipe, do we have any questions so far about this telescope?
We have a lot of readings or comments about different parts of the world. We have a hello from Billy View, from Thailand, uh, from Isa, from Amsterdam. We have a lot of readings and comments. Thanks so much for in advance for your time for the tours. Remember, you can leave your questions everyone you want about 3.6 meter telescope or about astronomy. Farid and I be astronomers, have a degree in astronomer to diffusions eh, to diffusions for science. You can ask questions when you want. So leave your questions for the moments we pause. So we have any question in that moment, but in the next time, in the next past, maybe we have some.
Okay, thank you, Felipe. We are going to wait for some questions during this tour. So now we are going to move to another location. We are going to leave uh, this dome. We are going to leave the 3.6 meter telescope, and we are going
Uh,
to continue with the next one. Yes, Felipe?
Remember, for the people, you can visit this place. You can visit that place. You can visit Paranal. You can you can go to La Silla and sit there in person in front of you. You can see the 3.6. Remember, in ESO.org, you can uh, reserve one day in a Saturday every Saturday in a years, and you can go to the La Silla or Parana, whatever you want.
Okay, thank you, Felipe. That's correct. So I hope some of the virtual visitors can someday visit in person one of the ESO observatories because we have free visits for the public. Okay, so now we are again outside. We are in the main mountain of La Silla Observatory, and we are just about to begin the next stop, the NTT telescope, the New Technology Telescope. But before, I would like to highlight the differences between the domes. Keep in mind that both telescopes have almost the same mirror diameter. So look at this dome. This is something like a classical dome with this shape, this structure. And the next stop will be the new technology telescope, and from here you can see something is different, right? We can see that something is different in this structure. So we are going to take a look in a few moments, but please take in mind that this mirror inside and the mirror inside of this one are more or less the same. Okay, but this dome, this structure is much bigger than this one. And this is basically a very good evidence that when the technology is doing some progress, we can improve the techniques to 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 build a more compact structure or enclosure for a telescope. Okay, so we are going to take a look at NTT. The NTT was inaugurated in 1989, and it has a small and very compact octagonal dome with a system of flaps. This represented in its days an evolutionary leap in the construction of telescopes, since it allowed hosting instruments in smaller, lighter structures with improved airflow on the inside. So gone were the more classical and massive domes, such as the 360. In fact, the flaps of the NTT allow air to flow smoothly, reducing turbulence and preserving the sharpness of pictures. Okay, so we are going to take a look at the NTT. Uh, Here we are. This is the internal structure of the NTT. You can see that this is a much more compact facility, and basically the telescope fits exactly in this location. So, do you remember the structure of the 360 telescope? It's huge dome, and how small our colleagues seem inside. Well, in this case, the building is practically attached to the telescope, and if we stand in front of it, we will look approximately this size. Okay, so um, the telescope mounting is also completely different. Here, the entire building spins around 360 degrees. So all of this will rotate. Okay. You can see the main mirror on a pale color round structure. We can see the mirror there. Okay. We can see the surface there. Okay. Now, the disk, this disk is the mirror, and we can see that it reflects some light. So do you remember the 53 centimeters thick mirror of the 360? Well, the NTT mirror has almost the same diameter as the 360, 3.58 meters to be precise, but it is significantly thinner. The mirror is only 24 centimeters thick. It is also much lighter, 6 tons. So this is more or less just one elephant. Okay? So to keep the perfect shape as the telescope moves, there is a system of actuators or pistons below the mirror. Okay, so this system is enclosed. This is basically this system is enclosed inside the box that you will see just below the mirror. Okay, here. So we have basically 75 actuators going up and down to keep the perfect concave shape of the mirror. This system is computer controlled and is called active optics. So the active optics was developed by ESO and represents a significant technological breakthrough in the construction of the next generation of telescopes in the 10-meter category. Active optics has been applied to all large modern telescopes, including the Very Large Telescope at Paranal Observatory, and will be included in the upcoming Extremely Large Telescope, or ELT, that is currently under construction near Paranal in the Armazones Mountain. And where's the staff? Well, around 30 people work in La Silla on different telescopes and tasks. Okay, um, I will show you quickly uh, the entity from this different view, just to let you know. Well, we have about 30 people working in La Silla on different telescopes and tasks. The scientific and technical staff are working from the control room of La Silla Observatory. So basically, they are not here. They are not inside of the telescope, and they are not in the 360. They are located in another room. They are located in the control building, in the control room. So the control room is located in a separate building quite far from here. So now we are going to take a look at a short video, short animation of the control room of La Silla
Wait
Observatory.
a wait a little moment before pass to the control room. I have a particular question about the inside of the domes.
Okay.
Jürgen von Mario asked, "Do you have air condition in on the dome?"
Well, as far as I know, in La Silla, they should have some kind of air conditioning, but the most important thing about the, the temperature, the temperature is something very important and critical when you are working with a telescope, because you need to avoid some kind of condensation. You want to avoid um, thermal turbulence inside of the telescope, because you need to remember that we are in the Atacama Desert, and during the day it's very hot and during the night it's very cold. And basically, the hot temperature is a source of thermal contamination. So when you want to uh, yeah, when you want to preserve a specific temperature in this dome, yes, you need some kind of air conditioning system. But the most important thing is that the air conditioning system is preserving a temperature that is more or less the same of the temperature of the next observation night. So, for example, during the day, maybe you have 25, 26 Celsius degrees, but during the night, you are expecting to have maybe 10 Celsius degrees. So, the air conditioning system during the day will be at 10 Celsius degrees in order to avoid a strong difference of temperature when the night comes.
And we have a question of Laura. Say, you showed my mirror as a protection for dust. You can see that in the front. But does it need a regular cleaning and maintenance? How is that done and how often? Gracias y saludos. Gracias y saludos para ti too. So, in particular, the entity you can see in the front. Farid, you can close to the mirror. You can move closest to the mirror, please.
Yes, yes, sure, sure. I will do a close up.
You can see these circular parts. This is a protection from for dust, so you can protect the mirror. But the maintenance of the mirror, in particular in NTT and in the 3.6 telescope, we have two methods. The first is a regularly clean, mainly carbonic snow. It's a liquid like a how it says spoon, like similar to clean the wheels of cars. So the people leave the carbonic snow, move around the mirror and clean clean itself. And the other method is the less common method for cleaning is a realuminescing maintenance. Around 2 years, around two around 2 years per years, 2 years, the mirrors of the telescope remove and move to the 3.6 and put in a, a similar to oven to remove the the fine cap, the fine surface of aluminum, and put another new one, so the mirrors can make a new mirror, fills the new mirror, and put the back to the corresponding telescope. This is two methods to cleaning a mountain scene. One is regularly, about 2 or around 2 weeks, and the other is around 2 years, the real luminescing method. This is a good question about the mountain scene. And sorry for that, but to continue for continuing the visit, later we can ask the another question, and we have a little surprise later. So you can continue for it.
Okay, thank you very much, Felipe, for this. Okay, so we can continue with the tour, and later we can continue answering some questions. So, Felipe, I don't know if you have the video of the control room
That's
at
right.
La Silla Observatory.
That's right. We have a video about the control room here.
Okay, thank you. So yeah, as you can see, this is something like a time lapse of the people working at La Silla. As you can see, it's not it's not a super big office. It's just an office space for the people working here. I don't know, Felipe, if you can correct me. The workstation to the left is for the 3.6, and the office to the right is for the NTT.
The left is entity and the right is 3.6.
Okay, thank you, Felipe, for clarifying. Um, so yes, this is the control room, and you can see that we have not a lot of people. We have some person in charge of the telescope operation, the telescope operator, and we have probably a few astronomers that are people from ESO, and they are in charge of all operations doing it all night. So basically, they have to be there all night, and but it's very exciting work, because they are basically doing science there. And you know, from La Silla, most of the time is completely clear, so they are working all night because all the night is clear, no clouds, no problems for the observations. Okay, so well, now you know about you know a lot of more information about the observatory and the staff who work here. So now I want to invite you to take a look at the main scientific milestones obtained from all ESO observatories. That is from La Silla, Paranal, and Jacnantor. So Felipe, do we have a video about this?
Yes, we have. So let's go.
Thank you.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so that was the top 10 discoveries, but we have something else. We have an extra result, something like a bonus track. So please, Felipe, do you have this to explain?
Yes, we have here.
Thank you. Thank you. So in 2019, a team of astronomers captured the first image of a black hole. So basically, the Event Horizon Telescope, or EHT, basically an array of 8 ground-based telescopes distributed across the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole. So in this case, the image reveals the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light years from Earth and has a mass of 6.5 billion times the mass of the Sun. So this is the picture. This was a very famous picture a few years ago. And that's it. Well, I hope you liked the top 10. Those discoveries achieved by ESO telescopes and the scientific staff are truly amazing, right? Okay, so now we are going to continue and we are going to move to another stage of this visit. So now we are going to visit La Silla at night, okay? We are going to change this beautiful view at night from La Silla Observatory. So as you can see, we have this fantastic view of the Milky Way. We have a lot of stars there, okay? But something I want to point out here is that this glare here and other glares there are light pollution. And this is a very important problem for astronomy because this is a problem when you try to observe the stars and you have something contaminated the sky, artificial light sources. So it's important to keep this problem under control because the main reason of why the observatories are located in the north of Chile is because of the very dark and clear skies. So it's very important to preserve these conditions, and that's why it's so important to keep the light pollution as low as possible. Okay, so maybe Felipe, can you tell me if this is Vallenara, as far as you know, Vallenara, and
That,
this
that's
maybe
right.
is
This is the
okay.
light of the right light is a Wegener, and the left part is the root 5, ruta 5. And
Okay,
in the back
and
you can see the Coquimbo light pollution.
okay, and the big light here is La Serena, right? Can you confirm?
That's right. This is
Okay.
Coquimbo La Serena city.
Okay, thank you. Thank you. Okay, so we are going to take another look at the La Silla at night. So here you can see this is a very nice view. And let me explain a little bit about this. So below, to the left of the NTT, okay, let's take a look. Maybe I have to find the right picture. Because maybe it's here. Maybe it's here.
Back to the entity, and later
Uh-huh.
in the back you can go to the night part.
In the previous picture, right? Correct?
That's right. In the previous picture entity, in the back you can press the button to the night part.
Oh, okay. Okay.
Or you can move in here place in the other part, right? Move to the right part here, and you
Mm-hmm.
can
Oh, yeah,
in
yeah, yeah.
the back.
That's correct. That's correct. Yeah. I think this will be useful for this in this case. Okay, I want to do a close-up here because we have a very interesting constellation here. So, does anyone recognize this? This is Orion, the Great Hunter, with his characteristic belt here, also known in Spanish as the Las Tres Marías, Three Marys. Okay, so maybe tired, perhaps after a long journey across the sky, Orion will soon set in the western horizon. So the hunter and the great dogs that accompanies him, or in the constellation Canis Major, have been following a particular path through the sky, the Milky Way, our galaxy. So um, let me point to this star here because we have a very bright star in this location. This is basically the, the biggest, sorry, the brightest star in the sky. The name is Sirius, and it's located in a constellation called Canis Major. Okay, so basically, as you can see, Orion and Sirius in Canis Major are located very close to this path of bright and stars here. So all of this, as you can see in this picture, all of this, um, uh, let's say, band of stars, bright, and a lot of more stars. If you compare with this area of the sky or this area of the sky, this is one of the arms of the Milky Way. Okay, and the Milky Way is our galaxy. Our galaxy is really a huge flattened disk shaped as a spiral, but we see it as a band of light across the sky because of our viewpoint, since we are inside of this disk. Okay, so our Milky Way consists of around 200 billion stars and huge clouds of interstellar gas and dust. Okay, we can see them later as dark clouds that cross the band of light. The red clouds instead are made of hydrogen, the simplest and most plentiful element in the universe, from which stars are formed. Okay, so in this picture we can see very clear how we have some let's say clouds. We have different colors, and in some cases red. So this is a very interesting view of the Milky Way, and we can see that this at this in this picture is in the zenith. I mean, is just above the point of view of the observer. So this is the typical night at La Silla. Let me find another picture to take a look at the um, Magellanic Clouds, maybe. I will try to find this here. I try to. Oh,
Uh,
okay, okay, here.
here.
Yes, yes. Okay, so we can see here something else. Um, by looking at through the Milky Way, we have this couple of spots in the sky. Okay, so what is this? These are similar to clouds, but they are actually galaxies, satellite galaxies of the Milky Way. So this one is the large Magellanic Cloud, and this one is the small Magellanic Cloud. These are our closest neighboring galaxies are, and at the same time smaller than our Milky Way. The name refers to the records from Ferdinand Magellan, because this was an important person in history who did a circumnavigation of the planet on the 16th century. So at that time, he was unaware about what a galaxy is. So in the records of Ferdinand Magellan, he identified those spots as clouds, not galaxies. So that's why the popular name of those objects are the Magellanic Clouds. Yeah, but that's it. They are not clouds. Actually, they are galaxies, okay? Satellite galaxies. So today we know that galaxies are systems hosting tens of billions of stars, and that these are classified as irregular because of the shape. Okay, you can see that they are irregular in shape. These typical objects, the large Magellanic Clouds and the small Magellanic Cloud, they are typical objects of the southern sky. And they are also important because they can indicate the position of the south celestial pole, with which the apexes of an equilateral triangle are formed. So, however, maybe the easiest way to locate the celestial south, since in this hemisphere we don't have the North Star, is with the constellation of the Southern Cross. Okay, so here in this same picture, we can see the Southern Cross there. So I will do close up, and we can see that the Southern Cross is there. In this case, it's tilt, is more or less invert. Okay, but you can see very clear that this is the longer stick and this is the shorter stick. Okay, so in order to find the south celestial pole, we have to extend the longer stick, this one, 4.5 times and a half. Sorry, 4.5 times. Okay, so we have to project this longer stick. Okay, like 1, 2, 3, 4.5, and more or less here. Okay, in this in this position, more or less, we will have the south celestial pole. So as you can see, one way to identify this south celestial pole is to project the longer stick 1, 2, 3, 4 and a half, like here. But at the same time, this is also forming something similar to an equilateral triangle with the Magellanic Clouds. You can see? Can you see here? So we have two ways to find the south celestial pole. Now, if you look at the horizon, if you have the south celestial pole and you look at the horizon, if you outline a line, an imaginary line, and you look this way, you are looking at the south cardinal point. So this is very useful in case you need to use the stars to find your way. Okay, so basically, the south celestial pole, just to finish with this explanation, is the point around which the sky will seem to rotate in a clockwise direction from east to west. So we say this because well, the stars are not exactly rotating, is just the Earth rotating, of course. But this particular point is the point where the stars appear to revolve around. Okay, so this is the south celestial point. Okay, so if we continue exploring our Milky Way, we are basically take a look at what happens here, and we can take a look at the beautiful objects. You can see, we can see again the Orion. We can see again the Sirius,
Syria.
the clouds. You see these important areas of the Milky Way. So basically, we have a lot of interesting objects here, and you can see from this perspective as well. For example, this is a comet. So you can see that in places like this, it's very easy to spot important astronomical objects. This object, for example, is an open cluster. This is the Pleiades cluster. So this is located in the Taurus constellation. And in this case, this is very easy to recognize because you can see at least seven stars with your naked eye. Okay. Okay, so we are approaching the end of this virtual visit to La Silla at night. So
You can
now
press
I
the
think we
circle
can.
in the down part. You can press
Excuse me?
the circle in the down part to move the hotel. The circle, that circle in front of you.
Oh, yes, of course. Here, right?
That's right.
Okay. Okay, so we are going to take a look at the main road of La Silla. This road is connecting all the telescopes. Okay, the telescopes in operation and the telescopes that are not in operation anymore. And this road is eventually also connecting with the hotel in La Silla, because in La Silla we have a specific place for the astronomers, for the scientists, for the telescope operators to rest at night. So we are going to take a look here because this is a very beautiful place as well. And you can see that from this hotel we have we still have a beautiful view of the Milky Way. You can see how the center of the Milky Way is just above in the sky. It's very beautiful, it's very bright. You can see a lot of gas, a lot of dust. This area is wider, you can see. So this is the typical view from La Silla, from the southern hemisphere in winter time. So probably this picture was taken around June or July, because at this season, winter time, it's possible to see the center of the Milky Way and all the Milky Way in the sky. And here you will see this is the hotel. This is the astrophotographer who take the pictures. So you can see a general view of the hotel in La Silla. And basically the main facility for the scientists to rest when they are working here. I don't know, Felipe, if you can give some comment about this place because you know more about La Silla.
This place is a beautiful hotel. You have we have a pool room. We have a lot of food you can eat. It's a delicious food you can eat. And the most important, the astronomers, the people who work here, rest in nice rooms, so in the night can work fine in the with the best health.
Yeah, that's correct. Felipe, excuse me. Because we are approaching the end of this experience, I would like to answer the final questions. So
We
I
have
think we have a question from the person from Thailand, right? I think.
a questions about what I have a answer one of what of what sorry my tongue. I have a question answer for one question. What's the most distant galaxy discovered in La Silla Observatory? The most distant galaxy is a Sagittarius dwarf, discovered in 1977 in ESO and in the telescope of 1 meter Smithsonian telescope. It's about around 3 million of light years away. It's too far away. And let me share the other question.
Yeah, I see one
Um,
about the most effective method for discovering exoplanets.
that's right.
Um, yeah, yeah. So basically, we have a lot of methods for discovering exoplanets, but I can tell you that we have two specifically that are more successful. One of them is called the transit method. In this case, you are trying to find an exoplanet crossing in front of the star. So basically, you are taking measurements of the brightness of the star, and when the planet is crossing in front, the brightness from the star will decrease a little bit. But this will be enough to be detected by our instruments, and basically, you will see this as something that we call a light curve. So basically, in this case, um, uh, if you find a particular light curve for the brightness of a star, I mean something like this. I am trying to represent. I don't know if you can see something like I know you have the brightness of the star right here, and suddenly you have a drop in the brightness. You have a drop, you have a drop, and suddenly you have the brightness again like the original brightness. So this is a good indication that you have exoplanet crossing in front of the star. So this is the transit method, and you can find that there is a lot of exoplanets discovered using this method. And the other very successful method is the radial velocity, and this is the system that HARPS is using to detect exoplanets. So in this case, you can see how the star, the host star, is doing some kind of movement because the planet, of course, is attracted by the star, and that's why the planet is orbiting the star. But the star is also attracted in some way to the planet, and is showing this kind of far forward and back, and basically this situation means that I don't know, Felipe, if you can put the video again, please, to finish the explanation. So when you have this situation with the star, you can see that lines from the spectrum, the absorption lines, are moving to the left and the right. So they are going to the blue or violet end of the spectrum, and then moving to the red end of the spectrum. So basically, when the star is doing this movement, it's basically going in a certain way. Let's say it's going closer to the Earth, and sometimes are going more far away from the Earth. Okay, so when the star is closer to Earth, okay, the absorption lines are going to the blue end of the spectrum, and when the star is more far away from Earth, the absorption lines are going to the red end of the spectrum. So basically, when you have this situation with the absorption lines going to one end and the other end, this is basically a good indication, a very good indication that the star is actually doing this kind of um, back and forth because of the existence of an exoplanet. So this is called radial velocity, and HARPS is a very high specialized instrument in detecting exoplanets using this method. Okay, so just to finish, the most successful methods to find exoplanets are radial velocity and transit method. Okay, I think we are on time now, Felipe.
Yes, we are in time, and sorry
Okay.
for don't answer all questions. And thank you for your questions for today. And I maybe in the next week I try to respond the most part of question you have today. Remember, every Saturday we have a virtual tour of Paranal and La Silla. Today is in La Silla, and the next week will be in Paranal Observatory.
Yeah, that's correct. So, well, I would like to remind you that all this visit information, pictures, and materials are available on the ESO website, ESO.org. Um, and of course, we invite you to investigate more about ESO, about the observatories of ESO. And of course, if you have the opportunity to try to visit in person La Silla or Paranal, because we have a visits program, and you can join any of those observatories. So basically, you can investigate more in the ISO website to know when you can maybe visit Paranal or La Silla. Okay. Okay, so that's all from my side. I hope you enjoy it, and I hope you enjoyed this virtual experience. And I hope to see you in the next tour. It could be Paranal or La Silla, Spanish or English. So stay updated, and I hope to see you next time. Thank you,
So
everyone.
so goodbye everyone. See you the next week.